So I said I mixed up the scales in explaining the Ekman layer and the cyclonic and anticyclonic flows around lows and highs. So here it is, the planetary scale ageostrophic flow. These are again surface pressure fields. We will look at this again in the next few chapters. I think you have been exposed to this at some point. So we had the trade winds. We haven't done the circulation yet. We will, but there are these so-called subtropical highs where the air is sinking and the flow is obviously anticyclonic. So you have trade winds and westerlies, as I mentioned before. Here you have westerlies and then polar easterlies, so you have the subpolar lows. There is a huge body of warm water here known as the West Pacific Warm Pool, where air rises, very, very warm water, so evaporation, rising air, and convergence, and low pressure, and vertical velocities into the atmosphere, expansion, cooling, condensation, a lot of rain, right? So this region here rains about 5 meters per second. So we will see this again, but the point is that these kind of pressure centers are associated with ageostrophic flow, but these are now very large scale. These are the planetary scale ageostrophic flows. These also drag the ocean around and create subtropical gyres and subpolar gyres in the ocean, with friction between the winds and the ocean, obviously. So the ocean also has an Ekman layer, which we will see later on, and ocean also has a corresponding anticyclonic or converging flow. So you have water going downwelling, as opposed to other places where the water is pulled up. So you have Ekman pumping. Okay, when water is pulled up, it's called Ekman pumping. Ekman pumping is when water is pushed down, water is pumped down, and when you have curl, that's positive. So you have westerlies and easterlies. So if you curl your finger as the right hand rule, you get an upward curl. So there is Ekman suction. So water is being pulled up. So in the subtropical gyres, there is Ekman pumping, and thermocline and so on are pushed down. Okay. You can take a section through it from the equator to the poles, and dPds in the meridional direction gradient is less than 0 in both hemispheres, just like we had dt dy less than 0 because of the direction of the y-axis. Okay, so here you can try to see your geostrophic flows. You have pressure going from high to low, so wind would go from the high pressure to low pressure. You add Coriolis, so you should get easterlies here. The same thing here in the southern hemisphere. Winds are pushed to the left of the direction of motion, so you would have winds going from high to low, and Ekman would Coriolis would push it to the left. So you have easterlies in both hemispheres around the low latitudes, around the equator, around the ITCZ, which are essentially the trade winds, right? The northeasterlies and the southeasterlies. Here you have again winds going from high to low, and again you have being pushed to the right, so you have westerlies, and so on. Okay, so if this large scale zonal winds are in geostrophic balance, then where is the frictional effect? Because here we are at sea level, right? There should be friction at the sea level. That all happens here in the meridional winds. So you have strong convergence. So corresponding to this, you have easterlies, westerlies, and the meridional winds associated with them. So remember northeasterlies and southeasterlies, which we haven't seen yet, but they both converge into the ITCZ, the Intertropical Convergence Zone. Okay, so that gives you the Ageostrophic flow, and there is a divergence at the subtropical highs, as we said, anticyclonic flow and divergence in the atmosphere, right? Subsidence, divergence, but the ocean is being churned and experiencing a convergence. Okay, so that's how the ageostrophic flow at the surface works. Some of the historic characters, we mentioned Rossby already several times. Carl Gustav Rossby was a Swedish meteorologist, lived in the US at MIT, and did incredible amount of seminal work. So Rossby waves, Rossby number, Rossby radius of deformation, Rossby adjustment problem, and so on are all associated with his discoveries. His son Tom Rossby is an oceanography professor at the University of Rhode Island, who has done amazing work in oceanography. Jeffrey Ingram Taylor, the British scientist who first theoretically argued for the rotational effects on homogeneous fluids, and it was Proudman who showed it in the lab, I think in a rotating cylinder. So it's called the Taylor-Proudman theorem that we saw, where under certain circumstances the flow is rendered a stiffness or rigidity parallel to the axis of rotation, which also gave us the Taylor columns, right? So that's another important character. G.I. Taylor did a lot of fundamental fluid mechanics work, which we're not looking at here. Okay, so let's summarize the key equations in the XYZ coordinates and in the XYP coordinates for incompressible and for compressible. So this is the general equations. When we have incompressibility, things simplify, and when we have compressible fluid, we move to the XYP coordinate, right? So ZP here is unit vector pointing towards decreasing P. So that's something you have to carry in your head, that Z unit vector is heading pointing in the direction of increasing Z, but ZP is in the direction of decreasing P. That has some consequences, right? So the equations we had, grad is d dx, d dy, dz, d dz, the vector. Continuity turned out to be d rho dt plus grad dot rho u equals 0. The grad went missing here. Hydrostatic balance we derived was dp dz equals minus rho g. You can see that this table has several errors or misprints or whatever. Geostrophic balance was wow, maybe I shouldn't do this at all. Okay, f z hat u is minus grad z. Jeez. Okay, maybe I didn't see these mistakes in my version of the book, but this PowerPoint has somehow got things completely screwed up. Nonetheless, the thermal wind balance was 2 omega cross gradient of u. If this is the general form, equal to 1 over rho grad p cross 1 over rho grad rho. This is the baroclinicity vector, baroclinic vector that we talked about. For the ocean, incompressible ocean, we still remain in the XYZ coordinate. Continuity reduces to non-divergence, okay, and the hydrostatic balance reduces to dpdz equals minus rho g, the same. The geostrophic balance, you know what that is. So because the ocean density can be written as rho ref plus sigma, you can see that there is a rho ref here which went missing. So let's not bother with these at all. Okay, so maybe I'll include a table in the next podcast, but this essentially brings us to the end of the chapter. Those last two slides are kind of homework problems which I may end up doing later on. Okay, so ageostrophic flow at the surface at large scale, and we also saw the small scale ageostrophic or subgeostrophic flows. We will see how the general circulation gets set up. This chapter is all about large scale balances. So geostrophic balance, hydrostatic balance was already there, and then we derived Taylor-Proudman theorem, and then we derived the thermal winds, and then subgeostrophic flow. Okay.